welcome everyone. This is a joint work with Fabrizio Montesi from the University of Southern Denmark and Saverio Gianlorenzo from the University of Bologna. And what I'm going to present to you is choreographies as objects. And this is a novel representation of protocols that we're calling choreographies as objects. And with this representation in this work, what we will give you also is a compiler, a way to generate correct and idiomatic Java libraries to participate into these choreographies, such that every participant into a multi-party communication protocol is able to just use the library and take part into the protocol. And the underlying novelty that is enabling all these the new way to represent protocol and to reason about protocols and the new tools in order to manipulate and implement them is a new kind of type, a new sort of types, and that allows us to specify, to talk about how data is going to be moved, manipulated by all the participants in the protocol. And so let's start. What is the problem we are trying to address in all this work? Is an old problem that goes under the name of choreography compliance. And so let's focus on the first term, that is choreography. Essentially, a choreography is a decentralized coordination plan for concurrent system based on messages. There are variations that allows for different kind of interaction of communication, like shared memory, but for the scope of this talk and this line of work, we are going to focus on message passing. And so what are examples of choreographies in these under this definition? Well, it's quite old as a notion. For instance, one of the first one is the security protocol notation that is used to define security protocols. And here is an excerpt of this notation. What we are meaning with this expression is that there is a role A, that is usually traditionally short for Alice, is going to send a message to another participant of the protocol identified as B. And the content of this message is the encryption of some payload X with some, and the encryption key is some key, K. And another example, there are graphical notations like the message sequence charts that display, where here is there is an example of this notation. You have three participants, a user, an ATM, and a bank. And on the vertical direction of the graph, you have the evolution over time of the protocol, and the arrows, as before, are going to represent communication, the interaction between participants. There are also other notations that were developed during the years. For instance, the Web Service Choreography Description Language by the W3C consortium, and the approach here was to bring choreography into a notation that is at once human readable and machine readable. And what is at the base of this is XML, which makes it understandable to a machine, is formally specified. About the readability compared to, for instance, the Alice above notation we've seen at the beginning is something we can discuss about, but still it's something formal with a well-defined meaning. And other examples that are used a lot in the industry is the business process modeling notation from the object management group. There are also many, and I would say the majority to some extent, of protocols that are written in natural language, usually English. And this is often referred as semi-formal English, meaning that many of the terms, the vocabulary that is used in describing this protocol is well codified and restricted in order to try to to take it under control, the ambiguity of natural language. And what you find in these kind of examples here, in these kind of protocols here, there is an example, a fragment from OpenID. You will find a sequence of steps with sentences like the client sends a request to the authentication server, the authentication server authenticates the end user, and sentences like this. And then what is the problem of this coordination, this choreography compliance? That given this description in some notation or some natural language, a semi-formal vocabulary we agree on, we actually need to bring it down to some machines that are participating in our protocol, that are composing our system. And on this machine, we are going to have some actual program, usually written in some mainstream programming language. It could be C or anything. For the scope of this talk, let's assume is going to be Java. And then what do we have? We have the choreography, this plan for the interaction among all these programs and machines in our system, which is, as we were saying before, for instance, OpenID. So the choreography compliance is actually bridging the gap, this gray area between the choreography on the top and the implementation at the bottom. And this is usually carried out by experts or programmers, and that needs to either look at the choreography and then implement the program, or take some existing code and check that is actually in performing all the steps it's supposed to perform in order to play the given role, for instance, the client or the authentication server in the choreography. And this is what goes under the term of choreography compliance, bridging this gap between these two layers, the green and the blue layer. And it's actually a hard and pretty demanding problem in computer science and software engineering in general, because these kind of protocols, besides the fact that they are in natural language or in some formal notation, are usually big. For instance, OpenID is 84 pages, and there are a vast amount of possible interaction between all the endpoints in our system. So a vast amount of events we need to check to verify that we are actually implementing the choreography. And for instance, this is a quote from Peter O'Hearn that said that if we were even able to process 1 billion interleaving possible plays of this kind of interaction per second, it would take more than 3 million years to check all the interaction that goes into the implementation of OpenID. So it's impossible, impractical to actually go through all of them and check all of them by brute force. We need something smarter. And the thing that we think this is a very hard problem, besides the size, is that even if we take expert programmers, they often make mistakes that are thought as simple. There have been studies that have made survey of open source software on GitHub that have found that quite often there are some well-known mistakes that are made by even expert programmers. And the fact that this software then ends up in all the modern infrastructure, like from big data, cloud, all the infrastructure for Industry 4.0, the Internet of Things, means that these bugs, these very simple mistakes, are going to have a very big impact. And that's why we think that this is one of the most pressing problems in computer science and software engineering in general. And this attracted many researchers over the last couple of decades, and more or less all of them had this dream of taking the current situation of the choreography compliance problem and first say, okay, one issue that can lead to all these mistakes is that natural language has ambiguity. Let's try to replace it with some formal language in order to describe what is our choreography. And this language is usually centered around the notion of interaction, since it's going to describe how the various components, the various roles of the protocol are going to talk to each other, as we have seen in the examples, for instance, for the Alice and Bob notation or the flowchart graphs. Then the other issue in this flow is that bridging the gray area between the choreography and the endpoint implementation that is going to run into the machine has been done by experts or programmers. And what we want to do instead is have an automatic tool, some procedure that is able to either check code written by programmers or generate code for them or help them in this activity. Because we want a tool there instead of an expert, because if we can check that the tool is actually doing his job in this translation or in this checking, then we get, as a side effect, as a side product, that all the implementation that are checked or generated by the tool are going to be correct implementation of the choreography, meaning that they're going to do the actions, the interaction they're expected to do or are prescribed to do from the choreography. And after more than 20 years and more than 800 papers from very brilliant people from all over the world, what we have is a lot of partial and fragmented solutions. I don't have time to go through all of them and talk what are the issues with these that lead to the partiality and the fragmentation, but just to give you an intuition of what are the main problems, let's have a look at an example of how these kind of systems are programmed nowadays. For instance, let's put the shoes of a programmer that needs to develop some code that has to interact with a distributed authentication service and a cloud storage service provided by some company or some provider in the cloud. And for those where the program we are given their choreographies, what is the plan for interacting with these two services? And usually the provider of the service itself is going to give you, instead of the choreographies or with the choreography, a library that is going to be the client to consume the service. For instance, a distributed authentication client. And as programmers, we just need to take the library and use this common API, for instance, create a client as we're seeing in this snippet of code. Likewise for the cloud service provider. And then we can compose them in our code and use them as we are used to use any other native library of our code without having to think about the actual protocol, the actual choreographies. I mean, there is perhaps going to be a contract to abide in the use of the API, but once the API is fixed and we know what is the contract, we don't need to care about the rest. And this means that this kind of approach is quite modular, meaning it is composable, as we have seen in this example, and it is robust to changes, meaning that if the provider of the cloud storage decides at some point to make some changes in the protocol, like they need to exchange some extra steps, some extra messages between the client and the provider, and those changes are not going to affect the API, as programmer of the application that is using the service, don't need to care about these changes. We only need to download a new version of the library, recompile our application and redeploy it, and this is often done, can be automatized into a DevOps pipeline, so we don't really care about changes in the choreography, and this is what makes it robust. And this is where many of the solutions you find in the literature actually fail, because they tend to leak details about the interaction between the client and the cloud storage provider, in this example, to the programmer. We need to be aware of how our application is going to exchange messages. So if the choreography changes, I need to be aware of this, meaning that I cannot just download a new version of the library. I also need to potentially modify my code. And this is one of the main shortcomings. We had a look at this, and what we think is the main reason behind that this shortcoming, what breaks the modularity of what is actually happening right now in the industry, is that the two layers, the choreography and the implementation layer, have very different approaches. They talk about different things. One is data-oriented. It talks about manipulation of data. And the choreography layer instead talks about the interaction between our participants in the choreography, how they're going to send messages concretely. And this is what we observed in the current literature leads to breaking this promise of modularity. So what we observe is that we need these two layers to talk the same language, to have the same approach, since it's hopeless to have everyone switch from Java to some other new programming language we can dream tomorrow. The point we can attack, the only point where we have some hope to change, is the choreography layer. So what we mean in Choral, what we are going to do in Choral, and what we want to do in general with choreography as objects, is to answer the following research question, that is, can we express choreographies, can we express multi-party communication protocol in terms of data manipulation instead of interaction, as we have been doing for 20, 30 plus years? And Yes, we can, and the inspiration for this is rooted in logic, as with many things and new concepts in programming languages, and specifically from hybrid logic. So let's see, here is an example of a statement in some logic. Then we're saying that there is medical data about Bob, and this can be formalized in our logic. In order to talk about interaction and where data is, so express communication in terms of data manipulation, we need to say how data is going to move in our system. And actually, hybrid logic has the instruments, the mathematical foundation to allow us to express and talk and formalize this kind of reasoning. For instance, now we can say in hybrid logic, there is a way to formalize a formula to express that there is medical data about Bob at the hospital. And we can also use hybrid logic to formalize statements like, if you have some medical data at the hospital, then you can copy it to the university. For instance, there is some agreement between these two institutions, so we can copy data whenever we want freely between these two. Now, by composing these two statements in the logic, we can derive a new fact that now there is medical data about Bob at the university, because at any time we can just apply this implication to the first premise and obtain this conclusion. How can we translate this into Choral and into this methodology of choreographies as objects? Well, a statement like there is medical data about Bob would be expressed in a language like Java, saying, oh, there is a variable, there is data, and the type of this data, this variable, is medical data. So it's a box containing some medical data, and then here is called Bob data just for readability. In Choral, when we apply this hybridization of Java, what we need to add is information about the location where this medical data is. And we express this by extending the information over the type. So now it's medical data with information about where it is, at the hospital, like we did in the logic. Likewise, the fact that the second statement that if we have medical data at the hospital, then we have medical data, we can copy it at the university, is captured by a function with this type that says it takes as an input medical data at the hospital. This is described by this type highlighted. And whenever we provide this data to this function, we call this function over this data, what we get in return is medical data of a different type that now is located at the university. So now from the type of this function, we can capture, we can talk about how data is going to be, the fact that the data is going to be moved. We don't really care right now at this level of the actual implementation. It can be done, but what we can tell, what we encode in the type is that we are consuming data in one place and we are giving you back data of the same kind at another place. And by composing the two, now the fact that we have now medical data about Bob at the university, we just need to compose this function. So call copy, the function copy providing the data at the hospital, and the function copy is going to provide us with now medical data at the university. And what the Choral compiler, the tool, will give you, now that you have this language that allows you to specify how you move data from the hospital to the university in terms of data manipulation instead of interaction, is you can produce Java code, you can produce the actual implementation for the university and the hospital. And what the tool will do, for instance, for the first line, is going to produce a line only for the program that is supposed to be run at the hospital. Because in this line, we're only talking about medical data at the hospital. There is no information about university appearing in the type here. So the tool is not going to generate anything for the university because there is nothing to do there for the university program. The second line, here we have the function. At the hospital, what we obtain is a function that will consume some medical data and then will give us nothing in return, because the return type of the function only talks about the university. Likewise, at the university, we have a function that has no input, because at the choreography level, the input is only at the hospital and not at the university. And the output instead is medical data. So this is the signature you expect from a receive, a function that you can call to get something back without providing anything. And finally, the composition of the two becomes at the hospital just a call to ascend. So we provide the data, we don't get anything back. And at the university, instead, we call this function without providing any information, and we get some data back we can store in the variable for Bob. And this is a very simple example, but I already showed you what is more or less the gist of all this Choral and all this methodology of choreographies as objects. And to have a look at an example that is a textbook example of an actual protocol using security. Here we have an implementation in Choral of the Diffie-Hellman key exchange protocol. So here we have a class, an object called Diffie-Hellman that is talking about as two roles, Alice and Bob, and each of them has his own private key as expressed in the following two lines. And there are some other information like a shared generator, share prime, and constructor, and etc. that I'm not going to go to describe in this presentation. And then the actual protocol is implemented into this method called exchange keys that is going to return as a pair of keys, one at Alice and one at Bob. And the first step is to compute the public keys. And here we have two lines where in the first line we have Alice that is calling some function x for exponential and providing some parameters, the shared generator, the private keys, and the shared prime. And what we get from it is a key that is located at Alice. Bob is not involved in any way in this line. Likewise, in the second line, we have another method invocation that will return some public key located at Bob. And there is no mention of Alice. Something that I would like to point out is that since the exponential is a method invocation to a method of the class, if this method is actually implemented in the class, what we are doing in this choreography is we are specifying in the protocol itself how the exponential must be computed. We are giving a reference implementation for the exponential function. If we leave it as an abstract method, for instance, it means that we are not going to specify it in the protocol. We are leaving it open, but this means that in Choral we can provide a reference implementation. We can actually tell what are the computational steps of the protocols in a very fine detail, and moreover in something that can actually be executed in a machine. The second step is the exchange of the keys, where Alice is going to copy his keys to Bob, and then they are going to do the reverse. So we are copying Bob's keys to Alice. And here again, copy could be a method of the class, meaning that it must be implemented by the class, so we can specify how these copies actually works. But in many general cases, what we are interested in doing is actually leave it as a hypothesis, a parameter of the choreography, which means that it can be a parameter of the method. And this allows the programmer to specify what are the hypotheses on the communication in this case using types. So we can internalize the capability of communicating data between Alice and Bob as an object called channel in this case, with a type that is a symmetric channel between Alice and Bob. And using different types, programmer here can specify different hypotheses on how data is exchanged between participants in a choreography. For instance, in another scenario, we want to ask anyone that wants to participate in the choreography to provide an encrypted channel or a channel with a logging facility or an auditing facility, and it can be internalized using different types and can be composed as in any other programming language. And the final step is to compute the actual shared key once we have received and completed the exchange. And then finally, we can return the pair. So now that we have this choreography written in a language that really looks kind of like Java, besides this annotation about locality, we can invoke the compiler, the Choral compiler, that is going to check the choreography for some common errors and mistakes or data handling issues. And then it can generate a library for us, for instance, in this case, Alice. So given our choreography here, what we get if we run our compiler is some Java code that we can run in order to play the role of Alice in a run of the Diffie-Hellman exchange protocol. And as you can see, is really similar. What we are losing are the parts that are talking about Bob, the lines about Bob, and the steps that Bob has to take. We only have the steps for Alice, but the important part is that the API is preserved. We still have a method called key exchange keys, and we are not leaking to the user of that method, of the user of this choreography, what are the actual steps of the implementation. If tomorrow we want to add a fourth steps, I don't know, for whatever reason, this is going to remain inside the implementation of the method exchange keys. It's not going to be leaked to the user of this library. And we run some empirical evaluation of what are the benefits of this approach. We observed a reduction in the number of lines of code that a programmer needs to write in order to participate, to implement a choreography, between 50 and 400%, and the different size depends a lot on how many participants there are, but still is a considerable reduction in the number of lines we need to write, the number of lines we need to check, and also the number of places where there are potential bugs. And so there was an initial study, but already highlights some of the potential of this approach. For starter, we think that there is potential to have a platform for the adoption of choreographic programming. And there are ongoing and past European projects on this topic, like Corevolution, Chores, or Be Happy inside the framework of Horizon 2020, and that are working on addressing the choreography compliance problem. And we think that Choral brings strong tools to address this problem. We also had interaction with people involved in these projects that confirmed our impression. And another big potential for adoption is by a researcher doing research on protocols, because so far there have been many abstract protocol models you can reason about protocols with. Choral is yet another one, but what you get with Choral is a reference implementation, which means you can run your protocol, you can already do tests, you can be very specific about the computation steps that are required in the protocol. And this means that one, it lowers the bar for adoption of the protocol you write by actual implementers and the industry, but also to the scientific community, means that all your studies becomes easier to reproduce, which will build confidence in the results and helps also assess the quality of this important branch of research. Another big potential is that since what we have is essentially Java plus some syntax to talk about where data is and how data moves, we can reuse a lot of years and investments that have been done in the analysis of Java applications. For instance, we can take tools that do taint analysis for Java programs, just erase the annotation with @Alice, @Bob, and use the very same tool in order to do taint analysis for Choral, for these choreographies, essentially getting for free or almost for free decades of tools and resources that we have developed for the analysis of local languages that we can now apply to protocols. There is, of course, potential in teaching. We're using Choral in some courses about distributed system. There are plans for evaluating the experience for students and how easy it is to use this language, actually. And again, what is the main potential we see, and also what was the main motivation for this line of work, is to improve the quality and reliability of connected systems in general. And with this, I thank everyone for your attention, and I invite you to go to the Choral website for more examples, more test cases, and details about this language, this theory, and all the mathematical foundation behind this approach.